Hey everybody, I'm Ankit Chandra from University of Nebraska, Lincoln, and it's a pleasure to share my research with you all today. Let me start with giving my research overview. There is a great agricultural and irrigation potential in Sub-Saharan Africa. However, only 4 to 6% of the farmland in Sub-Saharan Africa is irrigated. Many smallholder farmers remain poor because they are dependent on rainfall, making them vulnerable to impact of climate changes and lesser production. Now, these downsides of less productivity can be eliminated by mechanized farming. And this brings to my first point, that is considerable expansion of irrigation is important. Now, mechanized irrigation is costly and most of the farmers cannot afford it. So the government and external institutions design and invest in these projects for a larger group of farmers, which they call as irrigation scheme. And mechanized irrigation scheme is becoming a common approach for irrigation development in sub-Saharan Africa. However, even after developing mechanized irrigation scheme, there is a lack of quantitative data in terms of performance assessment due to very limited research and development in the sub-Saharan Africa region. And this is where our study comes in. Our study focuses on government-funded irrigation scheme for small landholder farmers, which accounts for roughly 50% of the irrigated land in Africa. Specifically, we assessed performance of a large mechanized irrigation scheme in Rwanda, which is called Kajitumba irrigation scheme. So the overarching goal of our study is to assess the performance of a mechanized irrigation scheme using real-time water and energy use data. The performance assessment was done considering these four main objectives, which are listed here. The first objective was to analyze the observed irrigation decision making, which will show the irrigation behavior to inform the recommendations. The second objective was to compare the crop water requirements to actual applied water. Our third objective was to evaluate the performance indicator based on water and energy use. Indicators such as crop water productivity and energy productivity were calculated and compared with local and global averages. Our fourth objective was to perform econometric modeling to understand the energy and food relations. Now here is an illustration of water energy food linkage, which I used in my analysis. Food was measured in terms of actual crop yield. Water was measured in terms of rainfall, crop ET, irrigation, and soil water change. Energy was measured in terms of direct and indirect energy. And each of these measurements were analyzed on the respective components to understand this connection. For example, we did regression analysis to understand the water and food connection. To understand the energy and food connection, we performed econometric modeling. And these interactions were studied using agronomic, engineering, and economic approach. So the Nexus approach helped in systemization of planning and decision making. Now here is a schematic diagram summarizing the methodology developed to study water and energy use. As you can see, the water food nexus on the left-hand side and energy food nexus on the right-hand side. First, I will talk about the water food nexus. Here is a schematic diagram summarizing methodology developed to study the water use and energy use. As you can see, on the left-hand side is the water food nexus, and on the right-hand side is the energy food nexus. So first I will talk about the water food nexus. To assess the performance, we estimated crop ET. For reference ET measurement, we used Hargreaves summary method and a crop water model. Crop coefficient were obtained from FAO 56. Now we come to crop water productivity. Crop water productivity was calculated as a ratio of crop ET to crop yield. For that, crop yield and crop type were collected from each pivot from the field. Now applied irrigation was measured during each irrigation event at the pumping station for analyzing irrigation decision making and other statistical analysis. We also calibrated irrigation water and energy use for each of these pivots. Coming to the energy food nexus, for the energy analysis, both direct and indirect energy were included because both of the sources incurs a considerable cost on the agriculture production. Direct energy is the energy that is directly embodied in crop production from a power source. Example, electricity used for pumping irrigation. And indirect energy is the energy embodied from different farm operations such as labor, machinery, energy stored in seeds, chemicals, and fertilizers. And these estimates were used for calculating the performance indicators and doing the econometric modeling. Talking about econometric models, so these are used to quantify the relationship between dependent and a number of factors that affect the dependent variable, which is known as explanatory variable. For example, if you look at the schematic diagram on the right-hand side, different energy inputs are listed which were explanatory variable. The crop yield is presented on the left-hand side, which is the dependent variable. And the same framework was used as a model to establish the relationship between crop yield and energy. We used a Cobb-Douglas production function, which is a popular functional form. So a couple of models were developed to study the yield and energy relationship. Moving on to the research site. Our research site is in northeast Rwanda, close to a village called Kajitumba. Now, 80% of the farmers in Sub-Saharan Africa are small landholders, averaging 1.5 hectare area. And specifically in this region, 80% of the farmers have less than 1 hectare of land. So a big pivot cannot fit with a small farmland. So shared model of irrigation was utilized in Kajitumba irrigation scheme. In this slide, I'll talk a bit about season, crops, and climate in Rwanda. So as you can see on the left-hand side, there is an illustration showing different seasons of Rwanda. There are three main seasons, A, B, and C. Major crops selected for this study were French bean, dry bean, and maize. And in terms of climate, Rwanda has a tropical climate where interannual variation is not very high. Soil type in the Kajitumba irrigation scheme specifically is sandy clay loam. Now moving on to our key findings. There are several findings, but due to time constraint, I have picked only key results to present here. My primary findings were about estimating and comparing crop water requirement for different crops. Maize, among other crops, has the highest crop water requirement. It is important to know the irrigation requirement in different development stages of crop. For example, if you look at the two plots here, if you look at the French bean graph, mid stage had the highest irrigation water requirement. If you look at the maize graph, late stage had the highest water requirement. And we will see how this finding comprehends with the irrigation decision making in our next slide. To analyze the irrigation decision making, we mapped the observed irrigation to model irrigation rate. The solid line here shows the irrigation applied, and the dotted line shows the model irrigation rate. In French bean, we found that irrigation applied almost matched with the model rate. However, if you look at the irrigation decision making in maize, the irrigation rate are staggered during mid stage and almost stopped during the late stage. So there is a gap between model irrigation rate and the observed field irrigation. But we saw in the previous slide that high irrigation is required during the late stage in maize. So clearly irrigation planning was not done. Similarly, in dry beans, 60 to 70% of less water than the model irrigation rate were applied. Our assumption was that farmers are over applying water because they do not need to pay for the energy cost as it is covered by the government. But on the contrary, our findings reveal that farmers are under irrigating in crops like dry bean and maize. One of the reasons of this could be that traditional farmers are being provided with mechanized system. So it's a challenge to use it properly for them. Now, to further see the impact of irrigation decision making on crop yield, we also did regression analysis, which revealed that irrigation positively impacted the crop yield. We also performed analysis of variance for water and food nexus, which revealed that Irrigation explained significant field-to-field variation in crop yield. Now, we calculated crop water productivity range for different crops and compared it with the global and local averages to understand the performance of crop. We found that the global average of crop water productivity for maize is 1.86 kg per meter cube, and any crop water productivity less than 1.25 was considered as low crop water productivity or need improvement for water management. If you look at the mean of crop water productivity in our study, it was 1.2, which means average maize crop didn't perform well. Now, there is a very little literature reported on crop water productivity in beans, so it didn't qualify for a global average study. Some of the research in Sub-Saharan Africa reported crop water productivity for French bean in range of 2.2 to 3.2. Now, if we look at the range of crop water productivity of French bean in our study, it varied from 1.5 to 4.5, averaging 3.3 kg per meter cube. So it clearly showed that the average French bean farms perform better than the local average. For dry beans, the crop water productivity varied from zero point 0.2 to zero point 0.6 kg per meter cube, which is similar as the reported crop water productivity for dry bean in FAO 33 paper. Some of the researchers in the United States reported crop water productivity of dry bean ranging from 0.4 to 0.9 kg per meter cube. So still there is a room for improvement in crop water productivity in dry beans. Now with the econometric modeling, we estimated the coefficient listed here. So we used a Cobb-Douglas production function in which coefficients represent the elasticity of dependent variable with respect to the explanatory variable. In other words, the coefficient is the estimated percentage change in the dependent variable for a percentage change in the explanatory variable. For example, what a positive coefficient here means is that if we increase the amount of irrigation in French bean by 1%, the crop yield would increase by 0.596% in these circumstances, keeping the other energy inputs constant. So in French bean, fungicide and irrigation had a positive impact on the crop yield, and insecticide had little negative impact on the crop yield from the given data. For dry bean, labor has a positive impact on the crop yield. For maize crop, use of tractor, fertilizer, and irrigation had a positive impact on the crop yield. In terms of overall impact, the finding revealed that both direct and indirect energy has a significant positive impact on the French bean yield, and indirect energy has a significant positive impact on the maize crop yield. Now, we also conducted catch-can test to evaluate the system performance and check the application uniformity. A catch-can test was conducted to evaluate this in selected pivots, and distribution of uniformity and coefficient of uniformity was estimated. In our study, the coefficient of uniformity was consistently less than 80% in the selected pivots. This means that the uniformity of irrigation by these pivots were in poor condition. As discussed in the results section, we found out that under irrigation across different farms led to significant yield loss in crops like maize and dry bean. Also, field-to-field variability in yield was explained by irrigation. So with decreasing irrigation, crop yield also decreased. Now, maize is one of the important cereal crop in Sub-Saharan Africa, and the analysis of crop water productivity indicated that the varied performance indicator was much lesser than the global average of crop water productivity, and that there is a huge potential to improve the crop water productivity, especially given the mechanized irrigation in the place. Techniques such as irrigation scheduling and educational efforts for farmers would be instrumental in improving crop water productivity. Econometric assessment revealed that irrigation pumping and fungicide input had a positive impact on French bean yield. Irrigation, fertilizer, and machinery use was found to have positive impact on the maize yield, and labor had a positive impact on the dry bean yield. In other words, there is a higher potential to increase the total output by additional use of these inputs on the respective crops. Now, the results reveal good performance for French bean in terms of irrigation decision making, crop water productivity, and crop yield. But if we talk in terms of irrigation system evaluation and other crop performance, the overall scheme underperforms, but still there is huge potential to improve the scheme performance. So with that, I will stop. Thank you very much. And I look forward to your questions, comments, and feedbacks.